Good morning, students. Today we are going to discuss some topics from solid state physics. The topics are the idea of amorphous and crystalline solids, the crystal lattice and translational vectors, unit cells, types of crystal lattice, and at last Miller indices. So all these topics are included in the first unit of the syllabus given by Guwahati University. So coming to the next slides, we have amorphous and crystalline solids. So solids can be classified into amorphous and crystalline solids. So what is crystalline solids? A solid is said to be crystalline if the various constituent particles like atoms, ions and molecules are arranged in a definite pattern. So if the constituent molecules are arranged in a definite pattern, just like as we can see in the diagram, we can say those solids to be crystalline. And if just the opposite happens, if the atoms molecules are they are arranged in a irregular fashion, then we can tell them to be amorphous solids. So we can see how amorphous solid will look like. None of the atom molecules are arranged in a regular pattern. So we can see some examples. We can see some examples of crystalline solid, that is NaCl. So common salt that we consume, so that is an example of crystalline solid. On the other hand, the example of amorphous solid will be glass. So glass that we can see in our window panes, so those glass are actually amorphous solid, and those glass are also known as supercooled liquids. So why it is called supercooled liquids? Because those liquids flow in a very slow rate. It behaves like a liquid, but the time frame is very long. That's why it's called supercooled. So if you want to realize that, we can go in a older buildings and then we can see the lower part of the window panes, they are thicker than the upper part. So it shows us that with time the liquid, that is the glass, has flown due to the gravity, and thus the bottom part is thicker compared to the upper part. So these are some examples and definitions of amorphous solid. You can take a screenshot and then you can write it. So coming to the differences, okay, sorry. Coming to the differences of crystalline and amorphous solid, the first difference is geometric structure, which we have already discussed. One is regular pattern, another is irregular pattern. So the second difference is melting points. So the crystalline solids have sharp melting points, whereas amorphous solid do not have a sharp melting point. They melt over a period of temperature. So as you can see from the graph, temperature versus time, we can see that there are two sharp points where the slope has been changed drastically. So this point basically shows the change in phase. So in those phase change, there is a distinct point where you can pin out that where the temperature has been responsible for transfer from one phase to another. Whereas in case of amorphous solid, we can see there is no such distinct points. Therefore, on the basis of melting point, we can say the amorphous solid and the crystalline solid varies in this perspective. The third point, we can say the crystal symmetry. So as we can see from the image, in the crystalline solid, we can see some symmetries in the crystal. For example, if you see, this pattern has been repeated 4 times. But if I want to imagine same thing in this image, then I will not be able to find out any pattern which is repeated. So therefore we can say that crystal symmetry is only observed in crystalline solid, but it is absent in the amorphous solid. Coming to the fourth point, that is behavior when cut. Now if I cut a crystalline solid, I will get a proper edge, just like if we imagine a cube, and if I try to cut it from the edge, then we will find out that we get a very defined edge But in case of amorphous solid, if I try to perform the same act, then we'll see that we get a rough edge. So on that basis also we can distinguish between the crystalline and the amorphous solid. Now the fifth point is heat of fusion. So just like temperature, crystalline and amorphous solid also have same behavior. Like for crystalline, we have a definite heat of fusion, but for amorphous solid, we don't have a definite heat of fusion. So coming to the sixth point, that is properties versus direction. This is very interesting because if you see in a crystalline solid, we can see that if I try to move along this direction, I'll find a number of atoms or molecules. But just adjacent to it, if I try to move, then I will find no atoms along that direction. So this mere fact gives a wide variety of property change in crystalline solid. But if the same thing if I try to see in a amorphous solid, we will see that even if I try to move from any point from the horizontal line, we will see that I will always encounter some atoms. Therefore, it will give me another set of properties. So so what that properties is called, we can say it to be isotropic and anisotropic. So those properties are seen in crystalline and amorphous solid. So if I say crystalline solid is more anisotropic, so in certain directions I will get a different properties, but in another direction I will get totally different properties just because of the regular arrangement of the atoms. Now let's see what is crystal structure. So crystal structure is basically divided into 2 points. Number one is basis and another is lattice. So what is lattice? So lattice is defined as a regular periodic array of points in space. Each point in a lattice has identical surrounding everywhere. So basically lattice is an imaginary point in space. So just lattice does not give us any crystal structure. So along with lattice, we also have to have a basis. So what is basis? Bases are atoms or molecules, the constituent atoms or molecules which will be present on those imaginary points, that is basis. That is lattice. I mean lattice are the imaginary points, and on those imaginary points we have to put basis. Only then we will get the defined crystal structure. So if you want to imagine, you can think of these lattice points. So these are imaginary points and this is my basis. So I have to put each of these bases on these imaginary points. If I do so, then I will get the crystal. So if I put a different lattice, different basis and the same lattice, then I will get a different crystal structure. So you can see my lattice are same in both the cases, but due to the difference in basis, I am getting different crystal structure. Okay, so I think this point is clear. So coming to the next point, that is lattice translational vectors. So translation means moving from one point to another. So within a lattice, if I want to move from one point to another, and if you are thinking in a perspective of three dimension, then we have to take 3 vectors, that is a vector, b vector and c vector, and these n1, n2, n3 will be the magnitude. So those magnitude will carry any of the integral values, and this ABC will be the fundamental translational vectors. So suppose I don't have a diagram here. So you can imagine, suppose if I want to move in the x direction, so in x direction if I have 2 lattice points, so the minimum distance between the 2 lattice points, that I can consider to be a vector. In y direction if I want to move, so minimum distance between 2 lattice points in y direction, that I can consider to be b vector, and c vector I can consider in the z direction, where the minimum distance between 2 lattice points will be c vector. So on that basis, I can, with the help of these 3 fundamental vectors, I can move from one point to any point within the lattice. So if I bring it down to two dimensional, then the translational vector will modify according to this equation, that is n1a plus n2b. Just the third dimension is missing, so the third term is also missing. So just like I was saying, so this along x direction we have a a1 vector, along y direction we have a a2 vector. So this is example of translational vectors, lattice translational vectors. So this is example. So I can consider another translation vector where I can take a1 dash and a2 dash, which need not be perpendicular, which may take a diagonalistic direction, but even then we'll get translational vectors. So coming to the next slide. So primitive cells and unit cells. Sorry, primitive cells and unit cells. So what is primitive cell and non-primitive cell? First we have to be clear. So if I make a cell where on each edge the atoms are present and there are no other atoms inside the cell, then we tell it to be primitive cell. But in this case we can see there is an extra atom present apart from these 4 atoms. So this will be non-primitive cell. So this is the basic difference between primitive and non-primitive cell. So these are the definitions, you can go through it. So now we'll come to the crystal system in 2D. So in crystal system of 2D, we have 4 distinct systems. Number one is oblique parallelogram. So how it is unique? The A and B vector, the A vector and the B vector, it will never be equal, and the angle between them, it will not be 90 degree. If this criteria satisfies, then we'll call it to be oblique parallelogram. Similarly, if we consider the angle between them to be 90 degree and A is not equal to B, then we'll call it to be rectangle. And in third case, if A is equal to B and gamma, that is the angle between A and B, is equal to 120 degree, then we'll call it to be hexagonal. And if A is equal to B and gamma is equal to 90 degree, then we'll call it to be square. So this is the system in 2D. So we have also crystal system in 3D. We will discuss in the next class. Thank you.